Good evening, children. So, in the previous session, we were enjoying, what should I say, spectra. We have thoroughly discussed about how emission spectrum is formed, how absorption spectrum is formed, how atomic spectrum is obtained, how does it look, line spectrum, and we have done molecular spectrum to be a band spectrum, and we have done many other aspects. Continuous spectrum, from an iron piece, heated iron piece, we got a continuous spectrum. So we exercised all such things: absorption, emission, band, line. What is common in all these things? What is common? Radiation is emitted by an excited body, or within a sample, if there are any excitations, de-excitations, we have got spectra. Means spectra is a set of lines, a set of bands, or a continuous impressions on a photographic plate. So where from all these things are coming? From the sample. So once you have a sample, it must contain atoms, because already people believed that everything is made up of atoms. Everything is made up of atoms, molecules, whatever. So electrons were already discovered. So the only question is what the electrons are doing in an atom, we don't know. So we now carry the game with spectral analysis. In the process, in 1900-1905, there were excellent revolutionary changes took place. That was blackbody radiation. Blackbody radiation means what? First of all, what is a blackbody? A perfect absorber and perfect emitter of radiation is a blackbody. Perfect absorber means again what? Suppose when you pass a radiation, it may not be able to accept all the lambdas. It may reflect some, it may absorb, it may transmit some. So it may not be a perfect absorber, every body. But if you can think of a body which is a perfect absorber of all the radiations that fall on it, it will make use of the radiations and then it will start emitting radiations, so that you can analyze the spectrum in a better way. You can analyze matter in a better way. So just select a body which can absorb many wavelengths, so that the analysis and the scope of the research would be more prominent. So let a body absorb maximum number of wavelengths within a range, of course. Then only it will be able to emit back. So that body is called a black body, a perfect absorber and a perfect emitter. Of course, we cannot find 100% black body in nature. Every body will absorb a part of radiation and transmit the other part, reflect. Anything may happen. You can visualize one particular body which is designed in such a way it may accept all the radiations. Like you take a hollow sphere, paint it inside with platinum black, a highly reflecting material, and let there be a hole. If a radiation enters into this, what will happen? It will hit this wall. Because a good reflecting material, it will reflect back, again it will reflect like this, it will reflect like this, it will keep on beating in the bush. So whatever radiation that enters it, it will be captured by the body. You can assume this as a black body. Later it will start emitting all radiations. So blackbody radiation has changed the outlook towards atomic structure. The features of blackbody radiation. What happened here exactly? Let us discuss now in this particular class. So, if you take a black body, let us say this is a black body, so it excited. What do you mean by excitation? The particles present in it get more energy. The other day I told you, to get an atomic spectrum, excite atom. To get a molecular spectrum, excite a molecule. What do you mean by excitation? Increase the vibrations, increase the energy, so that it starts emitting radiation. So, like that, a black body is heated to a good temperature, it starts emitting radiations. They won't appear, no, some radiations would come. By seeing it, you can't analyze anything. So, again the same story. Go back and go to the analyzer, pass it through an analyzer and filter the radiations according to their wavelengths, capture them on a photographic plate, and you can identify so many radiations have fallen on it, and each radiation with some intensity and some wavelength. So, this radiation may have some intensity, 1 means energy packed in it, energy density I1, and in this radiation the wavelength is found to be lambda 1. How to find out? Use a spectrometer and find the radiation's wavelength. Now, another intensity I2, there may be lambda 2, some other intensity, some intense radiation comes with some wavelength. Every radiation is associated with some intensity, some wavelength, different wavelengths, because it is a black body. It can emit so many wavelengths because it absorbed so many wavelengths. Absorbing wavelengths means what I mean to say. It absorbed various radiations with different wavelengths, and it started emitting radiations with different wavelengths. Different energies are coming out, different intensities, different wavelengths. Every radiation has got some intensity, brightness, energy packed in it. You see bright yellow, you see dull yellow, you see bright green, dull green light. That brightness, we call it intensity. So, intense radiations would come, and with different lambda. Some are dull with some other lambda. So, lambda and intensity we can simultaneously work out for every given radiation. And when these radiations are captured on a photographic plate, you get a continuous spectrum. My dear students, very important point. Black body radiations give a continuous spectrum. After all, black body is a solid. In the previous class, what did we discuss? Every solid gives a continuous spectrum, because all wavelengths are emitted, very close wavelengths are emitted. So, once wavelengths are very close on the spectrum, you will find all the lines formed on the very close to each other, which appears as continuous spectrum, just like your Yupp is a continuous spectrum. Will you find any gap between violet and indigo, blue kind of a thing? Nothing. So, it is a continuous spectrum. So, a black body radiations give continuous spectrum. It is from a solid. So, when you heat a black body to different temperatures, you will find different radiations coming with different wavelengths and different intensities. It happened, it is a fact, it is an experiment. So, immediately what happened? You can get the spectrum. Now, let us go for a graphical representation of black body radiation. Graphical representation of black body radiation. What will you represent in a graph about this radiation? We will take all intensities on y-axis, we will take all wavelengths on x-axis. Why we will take? They have taken. In atomic structure, we don't do anything. We only appreciate what people have done. That is the only story. For about 130 years, we just appreciate scientists and work out. We appreciate their work. We don't do anything else. So what they did, they got a curve, blackbody radiation curve, with all intensities of the radiations on y-axis and all the wavelengths of those radiations on x-axis. That has given an astonishing curve, which is just against to the classical physics beliefs. What people were thinking earlier was not happening with those curves. That curve has challenged many. The curve is a fact. It's a true fact. Truth. It's a truth. Because it is obtained from the blackbody radiation. So how does that curve look? Let us go through. We can say energy density on y-axis, and you can think of wavelengths on x-axis. Here low wavelength, here high wavelength, low intensity, high intensity, bright intensity, up, dull, low, left, low wavelength, right, high wavelength. Keep it in mind. Now blackbody radiation is a distribution curve. It's a distribution curve. Means what? You got a curve like this at some temperature T1. Let me say some 3000 Kelvin. Somewhere I heated the blackbody to 3000 Kelvin or some good temperature. It started emitting radiations. I recorded all the radiations on a spectrum. I got the wavelengths and intensities, and I showed them on the curve. First, let us understand, because you people are new to this kind of curves. These are distribution curves. If I keep a dot here, what is the meaning of that dot? There is a radiation that has come out of the blackbody with this much wavelength, lambda x wavelength. That radiation has got lambda wavelength, and that radiation has got intensity this much, I mean energy density. So if you go up high intensity, if you go down low intensity, towards this more lambda. Now one more radiation will take. Lambda is more lambda, more energy density. What did you observe? One radiation with less lambda is emitted with less intensity. Another radiation with more lambda is emitted with more intensity. Some more higher lambda, high energy density. Still higher lambda, highest energy density. Still higher lambda, again low energy density. Now people started breaking their head. What is happening till here? And what is happening till here? Till here, what is happening? With increase in lambda, intensity increased. Above particular lambda again, with increase in lambda, energy density decreased. Means what? Blackbody is emitting radiations at random. There are high wavelengths. This wavelength is very high. See how big a wavelength. Wavelength is high, but intensity is low. Wavelength is low, then also intensity is low. What should I conclude? Should I say with wavelength increase in wavelength intensity increase? Not happening. There are wavelengths higher wavelengths with low intensity, lower wavelengths with low intensity, medium wavelengths with high intensity are there. That is the behavior of a black body. Black body is emitting radiations with different intensities, different wavelengths. So, higher wavelength and lower wavelength are also having similar energy density. In that radiation energy packed quantity is same. And there is some other wavelength with high intensity, somewhere in the middle. So, what do you conclude? The curve is not either ascending curve or descending curve. Earlier with classical physics, at least we have learned, forget about intensity, energy decreases with increase in wavelength. As wavelength increases, energy decreases. As per earlier argument, classical physics, electromagnetic wave theory, we were believing that as a wavelength increases, energy decreases. But is that happening here? Of course, this is energy density, energy packed in a radiation. So, we have to be, it happened, people who are breaking their head, why this is happening like this? Why this is happening against what we believed as per classical physics? We have to change our mind according to what is happening, because that is a fact. No one can question black body radiation. You took a black body, heated, it emitted radiation. Black body is also a part of matter. So, it contains atoms. It emitted radiations. And radiations are showing this kind of random behavior. Low wavelength, low intensity. High wavelength also, low intensity. Moderate wavelength, high intensity. So, what should I say? We will see. Now, let us again appreciate what is happening. I think you appreciated this, some temperature T1, I will say. I heated a black body. So, intensity, energy density versus lambda. What do you understand from this particular small curve which gives lot of meaning? This represents the entire radiation emitted by a black body. Every point on this, every point corresponds to a wavelength. Every point corresponds to some wavelength. Every point corresponds to some intensity. Every point corresponds to a radiation, and continuous wavelengths are there. So, spectrum is continuous. Spectrum is continuous. Be, alert. So, these are all the outcome of a black body. It is emitting radiation because there is energy in it. So, what conclusions we can make out of this? Three best conclusions. Conclusion 1. At very low wavelengths, the radiations are having low intensity. At very high wavelengths also, the radiations are having low intensity. With moderate wavelengths, the radiations are having high intensity. So, most of the energy radiated by the black body means black body has lost energy in the form of radiations. Most of the radiations are having moderate wavelengths. See, this part you take, what are all those radiations? All these radiations, every point, very high intense radiations. Most of the energy is packed in these radiations. Very few radiations are having low wavelength, very low wavelength and high wavelength, very less radiations are there. See here, less. My dear children, students, try to understand. Every point is a radiation, representation of a radiation, graphical representation. So, most of the energy is distributed. High intensity means what? Lot of energy is stored in these radiations. They are all with what wavelengths? Moderate wavelengths. Are they high wavelengths? No. These are high wavelengths, these are low wavelengths, these are moderate wavelengths. If you take a company of 100 employees, all will not have very high salary, all will not have very low salary. Very 5, 6 will have very low salary, 2 or 3 will have very high salary. Most of the employees will have moderate salary. So, if the company is distributing salaries at the end of the day, at the end of the month, most of the amount will be going towards moderate salary people. The high salary will be taken by 1 or 2, very low will be taken by 5 or 6, 80%, 85 employees will take moderate. Means what? When you heat a black body, it emits most of its radiation. Suppose you have a hot iron piece, after some time what will it become? Cold. Means what? It has lost energy in the form of radiations. In those radiations, most of the radiations will have moderate wavelengths. Very few will have high wavelengths. Very few will have low wavelengths. Means what? With low wavelength and with high wavelength, very few radiations are emitted. Most of the radiations are having very close wavelengths, that too moderate wavelengths. Now, let us appreciate something. This at some t. What happened till here? As the wavelength is increasing till here, highest intensity is obtained. What does this radiation correspond to? That is the radiation with highest intensity. High energy is packed in that. That corresponding wavelength is called lambda max. Lambda max means what? The wavelength corresponding to the radiation with great intensity, highest intensity. Don't think lambda max is maximum wavelength. There are better wavelengths, higher wavelengths. High wavelengths means low energy. Low wavelength also low energy. That is the question now against classical physics. It shook the world, science world. Some small curve, Blackbody radiation. Now, let me raise the temperature. I got this curve. Again, the trend is same. At a higher temperature, definitely hotter radiations will be emitted. Suppose there is an iron piece at 1000 degrees, it will burn your fingers. Iron piece at 2000 degrees will almost burn on the spot. That is hotter, intensity is more. It emits greater intense radiations, high energy radiations. If you increase the temperature, obviously intensity will increase, bright light will come. Of course, it is a moderate common wavelengths. Here also the trend is same again. Low intensity, low wavelength. Very high, low intensity even at high wavelength. Wavelength is higher or lower, the intensity is low. If the wavelength is moderate, intensity is high. At this temperature also you have got a radiation with highest intensity and corresponding lambda max here. The lambda max decreases towards smaller wavelengths as the temperature is increased. Don't forget what is lambda max. Lambda max means what? The wavelength corresponding to a radiation with highest intensity, highest electron density, energy density. If I still increase the temperature, again lambda max decreased. backward. Shorter wavelengths are emitted, shorter wavelengths will come, high energy radiations will come. So, it is taking the support of classical physics. Somewhere something is happening, somewhere something is happening. What is that? How can you have two different wavelengths corresponding to same intensity? How can you have two different wavelengths corresponding to same intensity or same energy density, I should say, same quantity of energy packed with two different wavelengths? Means the black body is emitting a radiation with some good intensity, one more radiation with same intensity, but here wavelength is low, here wavelength is high. How come a low wavelength produced some energy density which could be produced by a high wavelength with same energy density? Classical physics against classical physics. Actually, classical physics supports uniform distribution of energy in a body. This is altogether a different. This is giving us a suspicion energy is not uniformly distributed. Random distribution of energy is happening. Conclusions, we'll try to infer something out of this. Now there is a problem. Now there is a trouble for us. What is the trouble? Why the curve is like this? It's a fact. So why it is happening like this? If we understand the problem, we will appreciate the solution in a better way. Now the problem is radiations are random. High wavelength, low wavelength, same intensity. Moderate wavelength, high intensity. Intensity is reaching maximum with moderate wavelength, somewhere in the middle. Lambda max is neither too high nor too low. That is the beauty of black body radiation. And with increase in temperature, intensity increases. Intensities of radiation, that is obvious. We don't have any objection for it. A red hot iron will give better intense radiation than a cold iron. As you keep heating a body, it will definitely emit intense radiations. Hai na? So, what to do? How to explain this strange phenomenon of a black body radiation? Had it been classical physics, you should have got like this. But you are getting up and then down. Till some wavelengths, intensity is increasing. After beyond a particular wavelength, again intensity is decreasing. With common energy density, you have got two different wavelengths. How all this is happening? What is happening in the body? Why it is radiating so wildly, randomly, disorderly emission of radiations? So there is nothing uniform inside the body. Something is happening. So who came to propose some beautiful postulates to explain black body radiation? In the beginning I showed you one flow chart, a big hierarchy. The black body radiation conclusions are well justified by the great Max Planck, who got Nobel Prize for his quantum theory. He proposed quantum theory in order to explain this wild behavior, strange behavior. It is usual only. For us it looks strange. It is not strange. For us it is, because we are biased towards classical physics, it looks strange. So then people started giving their imaginations. Then Planck proposed beautiful postulates under the name Planck's quantum theory. So let us see all that. See, 3000 Kelvin, low wavelength, high wavelength, moderate wavelength. At moderate wavelength, the intensity is a bit more. Means what? Most of the radiation is distributed towards moderate wavelengths. See, almost when you heat a black body to 3000 Kelvin, you are getting 500 nanometers radiation. 500 means what? 5000 angstroms. What is 5000 angstroms? Somewhere around VIBGR is between 3600 to 7800. If you take 5000 must be somewhere around violet, indigo, blue kind of a thing. Somewhere around blue up to 1000, 10,000. 10,000 means you have crossed red. Red is up to 7800. 10,000 means almost you have got infrared, thermal radiations. So, all these things. So, very high wavelength radiations are emitted, very low wavelength radiations are emitted, and somewhere in the middle some good intense radiations are coming at 300. And where is lambda max? Somewhere here. This is lambda max. 3000 degrees lambda max, 3000 Kelvin lambda max. When the body is heated to 4000 Kelvin, what did you observe? Again there is intensity raised. You know? So, lambda max decreased towards shorter wavelengths. At 4000 almost what are you getting? All radiations you are getting. These are all infrared which you can't see, heat radiations. And here you are able to see some visible radiations also. Almost you will get VIBGR, white light, which can split into VIBGR. This is a continuous spectrum. See, below 500 till somewhere around 7800 you can take, you are getting a VIBGR. VIBGR ranges from 3600 to 7800 approximately. So, when you heat a black body to 4000 Kelvin, you are getting light also. Of course, there are many radiations which are infrared, thermal radiations. See, to almost 20,000 angstroms. So, many radiations would come. When you raise the temperature to 5000 Kelvin, 5000 Kelvin, still lambda max decreased backward. Almost, here also you have got two varieties of thermal radiations are coming, visible radiations are coming, but with high intensity. So, as the temperature is raised, intensity also raised. But whatever may be the case, at any given temperature, you are having low wavelengths and high wavelengths corresponding to low intensities. High intensities are distributed at moderate wavelengths. See, these are all moderate wavelengths. Maximum intensity is stored. So, high intensity is distributed with moderate wavelengths at any given temperature. So, had it been, if you take classical physics, the curve should have been like this, 5000 Kelvin curve. What we expected, that what happened is here. So, to explain this, Max Planck proposed Planck's theory. What he proposed was wonderful. First thing, he gave a statement that why should a body radiate? Why should a body radiate? How can I teach if I have vibrations inside? I must have vibrations so I can speak some subject. Those vibrations are of course responsible to what I have learnt. So, I have learnt something, I got vibrations, so I am able to teach. So, similarly, in a body, black body, the particles present will vibrate with different wavelengths, frequencies. The charged particles, of course, what are the charged particles? Within any matter, nucleus is a charged particle, electron is a charged particle, and there may be some limitations inside the body. No one knows the atomic structure. I am speaking about 1905 story. So, people who are believing electrons will be present, that is all. How they are present, people who are not having any idea. So, Planck proposed the charged particles keep on vibrating. They keep on vibrating with different frequencies, non-uniform frequencies. That is where classical physics differs from quantum physics. As per classical physics, at a particular temperature there will be uniform distribution of energy, but as per quantum physics, Planck's theory, when a body is heated to a particular temperature, the particles present inside the body will undergo vibrations randomly, non-uniformly. So that the vibrations need not be uniform. So there can be different frequencies. Now you see different vibrations. These two are one vibration, these two are another vibration, these two are different vibrations, black are one vibration, nu 1, nu 2, nu 3. So these vibrations are responsible for emission of radiations. Emission of radiations. That is what the first point of Planck's quantum theory. Vibrations are non-uniform. And those vibrations are responsible for emission of radiation. The energy stored in a radiation depends on the vibration causing it. Why the vibrations are not same? Because the charged particles environment in the in the matter may not be uniform. Based on their chemical environment, structural environment, they may vibrate to different extents, and those vibrations are responsible for the emission of radiations from a body. Here he gave a vital point. These radiations are not emitted in the form of waves. Earlier we were believing electromagnetic waves are like this. We already spoke about this. Electromagnetic waves were believed to be like this. But what Max Planck says, the radiations are emitted in the form of energy packets. They won't release like this, they come like this. Energy packets are released. Every packet stores some intensity and wavelength. Different packets with different intensities, different wavelengths. Who decides wavelength? Who decides intensity? The packet name is quantum. And plural is quanta. Every packet is an energy packet, is an outcome of a particular vibration, a particular frequency of vibration. So, the energy of a packet is given by either h nu or nh nu. Nu corresponds to the frequency of the vibration of the charged particle in the body. But why there is n? At different such frequencies may occur with different particles, and sometimes those radiations may come together as a bundle. Suppose you take this red color thing, this is some frequency nu 1, this is also nu 1. So both will emit some radiation, and these two radiations may come together as a bundle. That is called quantization of energy. This frequency causes emission of radiations which may come out as packets, and those packets may be bundled. The bundling of energy of similar packets is called quantization. And this frequency is bundled. This frequency decides the energy, lambda, but this bundling decides the intensity. My dear students, try to love this concept. Lambda is different. I mean frequency. There we respect classical physics. No objection. Lambda and frequency are inverse relation. That classical physics is respected there. But what magic is happening in any body, what proposed by Max Planck, bundling of energy may take place. The frequency decides the wavelength, bundling decides the intensity. Energy comes out in the form of packets. Of course, later how they propagate in the form of wave and all, Planck did not tell anything. Packets are discrete packets. You may have a number of packets coming out. Each packet may have lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. All these lambdas are closely related because all are coming from same solid body. The vibrations may be close, so wavelengths, frequencies may be close. Frequencies are close, lambdas will be close. If the lambdas are close, you will get a continuous spectrum. Now, so each packet may be containing a bundle of radiations. That is why E is equal to NH nu. More the N, more the intensity. More energy is packed in a radiation. This corresponds to intensity of a radiation. That intense radiation will be there if more bundling happens. So, multiples of each quantum, that is called quantization. Suppose this frequency causes 3.2 electron volts. So, if two such radiations come together, so what will be the energy stored in this? 6.4. Because there are two 3.2 electron volts bundles, quanta. If 3 bundle, 9.6. If 4 bundle, what will happen? 12.8. So, it will be a multiple of 3.2 provided all the radiations are coming due to similar frequency. And there can be different frequencies, different wavelengths. Now, let us go back to the curve. You got something like this. Intensity, energy density, you can say, means energy packed per radiation. You can assume like that roughly. How can energy packed for radiation be two wavelengths, different wavelengths? As per classical physics, wavelength is always a measure of energy. How can different wavelengths represent same energy density? How is it possible? Means bundling is happening, quantization is happening. Hats off to Planck. High wavelength, low energy, low wavelength, high energy, classical physics. But why same intensity, energy density? Suppose high wavelength means low energy, 3 electron volts. Low wavelength, high energy, 6 electron volts. But how come they have same energy packed per radiation? Maybe, suppose 2 of this are bundled, 6 electron volt, 6 electron volt. So, what is the energy packed in that? Energy quantized twice. So, 12 electron volts intensity, energy density is there per radiation. Maybe this is 4 quantized. How much energy stored? 12. How much energy stored? 12. But are the wavelengths same? Are the vibrations same? This is such a vibration which will produce 3 electron volt radiation. This is such a vibration which will produce 6 electron volts. I may pack 200 rupees notes. Each one is a 100 rupee note, currency. 2 notes make the packet 200 rupees. But 4 notes of 50, some other fellow packed 50, 50, 50, 50. This is also 200. As a stored energy, both are 200 rupees only. But here it is a bundle of 200 rupee notes. It is a bundle of 4 50 rupee notes. Definitely individual notes have different wavelengths. 100 note has its own wavelength, 50 note has its own wavelength. They do different jobs. Lovely aspect is bundling. So intense radiation means more bundled. Red, some wavelength. Intense red, many wavelengths. Many such radiations put together, many such quanta put together. So my dear students, by seeing this, Planck proposed that. And the distribution is also random. This shows that random distribution of energy. Classical physics, uniform distribution of energy at a given temperature. Quantum physics, random distribution of energy. So energy is randomly distributed once you raise the temperature of a body. Different particles undergo different vibrations. And different vibrations emit radiations of different wavelengths. While coming out, they come in the form of packets. Those packets may be bundled, which will decide the intensity. That is Max Planck's quantum theory's postulates. So let us appreciate that now. At a given temperature, the intensity of a radiation emitted increases, reaches, this is Blackbody radiation features. At a given temperature, the intensity of radiation increases, reaches a maximum, then decreases. Actually, these are all distribution curves. Means what? Moderate to high, then high wavelengths, low intensity. It reaches a maximum at moderate wavelength, which is called Lambda Max. That's what this is. These are the features of Blackbody radiation. As the temperature increases, the maximum intensity shifts towards shorter wavelengths. Actually, when we increase the temperature, low temperature, Lambda Max is here. The temperature is high, Lambda Max is here. So as the temperature is increased, shorter wavelength radiations will be obvious. Once you raise the temperature, vibrations will become more severe. As the frequency of vibrations increase, more intense, high wavelength, high energy radiations would come out. Obvious. Obviously, intensity also will be more. Most of the radiation is distributed with medium wavelengths. Most of the radiation is with moderate wavelengths. Obvious. Most of the vibrations will be uniform within a body. Very few will undergo very severe vibrations, very few will undergo very mild vibration. So randomly, if I throw chocolates into a classroom, most of the students will get almost same number, nearly close number of chocolates. One may get more, one may get suddenly 20, one may not get anything, or may get 1 or 2. It happens. Very few will be there like that. The fellow who got very much and a fellow who does not get anything will be very less. Most of the students will receive moderate number of chocolates. Similarly, when you raise the temperature of a body, most of the vibrations will have moderate frequencies, so moderate wavelengths. Very few vibrations will be with very high frequency, very few will be with very low frequency. So, the curve is like this, less intensity at high and low, high intensity at moderate, black body radiation. Both shorter and longer wavelengths correspond to low intensities, which is contrary to classical physics. That is what we were discussing. Now, Planck's quantum theory. What did Planck propose? At a given temperature, every body radiates energy in the form of discrete packets called quanta. So, once you have a radiation, once you have a body, when you raise the temperature, it starts emitting radiation in the form of discrete packets. These packets are called quanta, plural. If a single packet, we call it quantum. The vibrations of charged particles in the body cause emission or absorption of radiation. So, who is responsible for the emission of radiation? The vibrations of the particles, charged particles inside the body. Those vibrations are severe radiation, high energy radiations will come out. Moderate vibrations lead to moderate energy emission. Each quantum is associated with a definite energy. E is proportional to nu. E is proportional to nu. So, greater the frequency of the vibration, greater the energy. But do not speak about intensity. Intensity depends on the multiplication of the quanta, bundling of quanta, quantization. So, more the quantized, high intensity radiation, yellow light, some intensity, too many packets, bright yellow light. So, here H is Planck's constant and nu is frequency. Planck constant value 6.627 into 10 power minus 34 joule seconds. Respect the scientists and remember those values. In hydrogen spectrum yesterday I referred one value, Rydberg constant. I did not speak much about hydrogen spectrum now. We will discuss about hydrogen spectrum after Bohr's model. I will not deviate from the hierarchy. Spectrum, black body radiation. Then black body radiation was justified, this curve was justified by Planck proposals. What did Planck propose? The energy is emitted from a black body in the form of packets. The energy of packets are quantized. Most of the energy is distributed with moderate wavelengths. Most of the energy radiated will have moderate wavelengths. Very few will have high wavelength and low wavelength. More the bundling, more the intensity. The bundling can happen only if the emission happens in the form of packets. So, that is called quantization. There will be only acceptable values for the energy of a packet. Of course, after emission they may move forward in the form of a wave. So, Planck only told mainly three things. Point 1, when you raise at a given temperature, the body undergoes vibrations of the electronic charged particles in the body, constituent particles, or mostly you can say non-uniform vibrations. The heat given to a system will be distributed randomly, just like chocolates I have thrown. Due to random vibrations, emissions are random, different wavelengths, different frequencies, but very close, because it is the same body and temperature is same. That is why you will get a continuous spectrum. All wavelengths will be recorded. And there can be bundling of the packets, so which will raise the intensity. So, E is equal to NH nu, 3 electron volts. Again 6 electron volts, 9 electron volts for one particular frequency. Suppose another frequency 5 electron volts, what will be its bundles? 5, 10, 15. It can happen, but basically 5 should be there. A 5 electron volt quantum cannot give 7 electron volt bundle. There is no chance, because 7 is not a multiple of 5. So a body emits light, radiation randomly bundling. That is the beauty of Planck's quantum theory. The energy of each quantum is quantized. This word we are going to listen many times, quantization of energy. So quantization means bundling and multiple of certain fixed quantity. The intensity of the radiation depends on the extent of bundling of the quanta. Whether it is a bright light or dull light depends on how good the bundling multiplication occurred. So all these postulates were proposed by Max Planck just to explain what? Blackbody radiation. So these three things you imagine. This is a hard body. The radiations gave these curves. To explain this, Planck proposed this, which has revolutionized physics. Beautiful aspect. People started thinking the other way. Now light is no more a continuous wave kind. It is discrete particle, quanta. Because we have seen light also in the curves, if you remember. See? This is light only. At 4000 Kelvin, when you raise the black body temperature to 4000, what did you get here? So till here, what are these wavelengths? Somewhere around 4000 to, this is nanometers, means multiply with 10, you will get angstroms. 5000 angstroms, VIBGY or no? Almost 4000 to 7500 red till red. Then you get heat radiation. These are all thermal radiations, heat. And below this you won't get. You can't get ultraviolet kind of a thing from a black body. So you are only getting this. So you are getting light. Light gives what? Continuous spectrum. The beauty of black body radiation is emission of radiations is discrete. The spectrum is continuous. The body is radiating in discrete packets, discontinuous packets. But all these packets cover most of the wavelengths, closely associated wavelengths. So all will fall at same place in the photographic plate and you are going to get a continuous spectrum. So black body radiation is discrete in nature, but the spectrum is continuous. Spectrum is continuous. These are all very, very important points students should remember. So what was the order what we have learned today? First we understood what is a black body, a perfect emitter, perfect absorber of radiation. So it catches up all radiations, it will start emitting all radiations. To emit, you absorb. And all those radiations are coming, producing some curve. This is the curves which has astonished the people, very strange. What happened to classical physics? So you have got different intensities, different wavelengths, everything is at random. And high wavelength and low wavelength with low intensity. Medium wavelengths, moderate and high intensity. What is this? So to explain this, he proposed postulates. Who? Max Planck. So hats off to the experiment of black body radiation. See, try to understand. We can't see an atom. We are getting the information what is inside the atom by means of radiations. By means of radiations. Now we are able to observe electrons are vibrating in the atom. Different frequencies. Why? Different chemical environment, different structural environments may be there. We already got spectrum, atomic spectrum, line spectrum. We already got Niels Bohr's, we already got hydrogen spectrum, like this. So this is how we appreciated blackbody radiation and the curves, and we explained the curves and their nature. Then we appreciated the postulates of quantum theory. Every body undergoes vibrations of the internal particles, due to which radiations would come. Radiations would come in the form of packets. Packets are called quantum, and each quantum is associated with E is equal to h nu. There can be bundling of energies called quantization. The intensity depends on bundling. Greater the bundling, high intensity. This is pertaining to a hot body. What did you see? 3000 Kelvin, 4000 Kelvin, 5000 Kelvin. You raised the temperature of a body. Somewhere you got light also, that 400 to 800, 700 nanometers. Now, Einstein has generalized this theory. Einstein has generalized quantum theory. Planck's quantum theory was confined to a hot body, or a body at different temperatures. At any temperature there will be vibrations. They may not be observable because if the vibrations are very low, we can't observe. If when you heat to 3000, you are able to observe some light. That's okay. Now Einstein says he extended the blackbody radiation not only for heat, for the entire electromagnetic wave spectrum. I hope you remember electromagnetic wave spectrum. This visible light, then infrared, you have ultraviolet, X-rays, gamma rays, cosmic, some radio. So you have got visible light, infrared, radio waves, microwaves, ultraviolet, X-rays, gamma rays, cosmic rays. Einstein has extended quantum theory for all the electromagnetic radiations. Not only a heated body, any electromagnetic radiation comes out in the form of particles. In the form of particles only. Suppose a bulb is glowing. These radiations, light, no, they come in the form of particles. Those particles are called photons. Energy of photon is E is equal to h nu. A photon has no mass. Photon's energy can be bundled. You can have a bundle of photons. So, high intensity radiation. Einstein generalized Max Planck's quantum theory, which was confined to heated bodies. Einstein has generalized it for every electromagnetic radiation. Why only heat? It happens with every source of electromagnetic radiation. My dear students, electromagnetic radiations, the radiations which move with same velocity, 3 into 10 power 10 centimeters per second, 3 into 10 power 8 meters per second. All electromagnetic radiations are emitted as particles from their source, propagate as particles, absorbed elsewhere as particles only. Say photon is photon, right from its emission, its movement, its absorption. Everywhere it remains its identity as a photon. Albert Einstein's generalization of Max Planck's quantum theory. He says a photon has E is equal to h nu energy. A photon has a speed c. A photon has velocity c. Einstein generalization. All electromagnetic radiations emerge, propagate and get absorbed in the form of particles called photons. So, there is a source of light, energy comes out in the form of particles called photons. The energy of a photon is given by E is equal to h nu. Photons may be quantized, that energy will be multiplied. Photon has no mass, photon has velocity is c. Photon has speed same as light. Every photon, red photon, blue photon, yellow photon, gamma photon, all will have the same velocity as light. So, from the source, hereafter we are going to visualize electromagnetic radiation in the form of particles, and each particle is a photon. How to calculate energy of a photon? E is equal to h nu. A photon has wavelength, corresponds to a wavelength c by lambda. So, E is equal to hc by lambda. Lambda is the wavelength of the photon, red photon, blue photon, gamma photon, anything you can calculate. Here our doubt is, why should we accept Einstein? He simply said every electromagnetic radiation. Earlier we were believing electromagnetic radiation is a wave. Electromagnetic wave theory, we appreciated electromagnetic radiation to be a wave. Now suddenly by seeing Max Planck's quantum theory, Einstein has generalized. Of course, Planck proposed his theory pertaining to explain the curves given by blackbody radiation. Einstein has generalized that for every electromagnetic radiation, complete spectrum. The energy moves in the form of particles. Electromagnetic radiation moves in the form of particles. Hereafter you treat light as particle. I am receiving light, I am receiving some photons. A bulb is glowing, bulb is emitting photons. You are keeping a torchlight, it is emitting photons. A radioactive substance emits gamma rays. It is also photons, particles. Don't call them gamma particles. Gamma radiation is in the form of photons, particles. Velocity is light velocity. But why should we take Einstein theory as granted? Planck proposed intellectually to explain the lines given by, the curve given by blackbody radiation. But what evidence Einstein has to support his proposal that light is particle? That is the great photoelectric effect which gave Einstein a Nobel laureate honor. So, photoelectric effect is the evidence. So, Einstein's generalization is not simple generalization. He did not just like that tell this. He has an evidence for it. That evidence is photoelectric effect. Photo means photon, light. With the help of light, get current, electricity. Use light, get current. Photoelectric effect. get electric current using photons, light. Use light, get photons. Sorry, use light and get electrons. Take a metal piece. Take a metal piece. Bombard the piece with metal piece with light, and electrons are ejected. A metal surface is bombarded with some light. Light, we will use the word light only at present, and it starts emitting. It starts ejecting light, ejecting electrons. Ejection means sudden release. So this is the experiment. We will discuss about it much more in our next class. So till today, you just read any standard textbook, preferably Atkins, like very standard internationally reputed books and national books, whatever. Just enjoy reading. Blackbody radiation, Planck's theory. Especially read about the importance of those curves, Blackbody curves, Lambda Max. Don't always think about examination only. Think of the work done, intellectual work done by the great Nobel laureates. You will appreciate science more. So my dear students, so just listen to the lectures again and again so that you will get more clarity. Take down the points and read the material what we have sent. If you have any doubts, we are there to answer. Use 24/7 doubt clarification platform and talk to us. We will meet in our next session with photoelectric effect, and Albert Einstein, some with numericals also will work out. Thank you. Have a good evening. Enjoy.